Great. In this video, I will very briefly talk about dependency graphs. So I'll show you some examples. Let's say I consider the joint probability distribution of x1 through xn. And let's say these are independently distributed. Then the probability will be the product of i's 1 to n and the probability of the ith guy. So this is the independence assumption I just said. So then the way I would draw this would be in the dependency graph. I would just draw one node for each random variable, and I would draw no edges because there are no dependencies. So let's maybe look at an example where there are some dependencies. Let's say I look at x, y, and z, w. And let's say that I have the probability of x, probability of y given x, probability of, say, what could do z? Let's do w actually given x, and then probability of z given yw. So let's just make it a bit clear. This was a w. Yes. So then, I mean, x doesn't depend on anything, so I'll just write x as itself. But then y dependent on x. So I'll draw an arrow from x to y, indicating that y depends on x. And this is just an x. Not an x1, it's just x. And w also depends on x, and z depends on y and w. So this would be the way of translating from the joint probability distribution to a dependency graph. So maybe let's try to do it the other way around now. Maybe I'll suppose I have maybe I have something, look, what could I draw? Maybe I'll draw something like this. This would be x1, x2, x3, and x4. Maybe let's draw something like this. Something like this. Then what would the joint probability distribution be? x2, x3, x4. So this guy doesn't depend on anything, so I could just write this guy, probability of x1. Then I know that x2 and x4 depends on x1, so I could write probability of x2 given x1. And then I know x4 depends on both of these guys, so I could write probability of x4 given x1, x2. And then x3 depends on that guy, so I'd write probability of x3 given x4. Great. So this is like an example of how you can translate back and forth. So now I just want to draw another guy. So let's say I have a probability distribution of x1 through xn, and this time it's the probability of x1, but then I have the product from 1 to n of x, actually I do this from 2, of xi given xi minus 1. So you can imagine, maybe I'll just try to write this out. What I mean here is the probability of x1, probability of x2 given x1, probability of x3 given x2, up to probability of xn given xn minus 1. So I'm just writing this last bit here as a product. So this is the same as this. So the way I'd draw the dependency here would be I'd have x1, and then I would draw x2. But x2 has a dependency on x1. I'll draw an arrow. And then I'll draw x3, but x3 has dependency on the guy before. I'll just continue doing these. So this will be the dependency graph of this guy. So now I want to, so now we went this way. Maybe let's try to go the other way. So let's say I draw something like, I'll have C1, C2, Z3, all the way up to Zn, and I'll have x1, x2, x3 all the way up to xn. So I'll have this dependency graph. So let's try to see if we can draw the joint probability distribution of this guy. Well, it would be, well, this guy doesn't depend on anything, so we could write this probability of z1. And then let's just start by looking at, well, this chain looks exactly as what we had up here before. So I can write the probability of z2 given z1, probability of z3 given z2, so on. So this would give me the product from I is 2 to n, and then I could just write the exact same thing here, but with z's instead of, so it's zi given zi minus 1 instead of the x's. But then now at each step I have a probability of xi given zi. So I'll have probability of x1 given z1 and probability of x2 given z2 and so forth. So I'll add this product from 1 to n of probability of xi given zi. And this will be the joint probability distribution of this dependency graph. Great. So now I showed you like how you can go both ways. And this is just like a visual representation of the dependencies we assume to be in this joint probability distribution. So I'll just briefly try to relate this to machine learning. So in machine learning, sometimes we have the identically and independently distributed assumption. So these guys are definitely independently distributed. So that's the independently distributed kind of assumption seems to hold here. So if these guys are also from the same distribution, so you might have like xi are distributed from some distribution d for I is 1 to n, then this actually captures the IID distribution. And if you read Bishop's book, he will also have a graph that kind of looks like this. So later in the book, he introduces this thing where he says that the ith guy, so let's say I'm looking at this guy, third guy, then this guy depends only on the guy before. He calls this the Markov assumption. So let's just write it out. So the probability of xi is given the probability of xi. Oh, sorry, this is so probability of xi given xi minus 1, xi minus 2 all the way to x1 is the probability of xi given xy minus 1. So instead of depending on all these guys, you just kind of erase them. This is the Markov assumption. So you don't depend on everything that happened before, you depend on only what happened before. So maybe if I do a brief example, we have rain, sunshine. We can have rain, sunshine, and maybe let's do one more sunshine. So this would be x1, x2, x3, x4, x5, x6, x7. So then the probability of observing rain at this day would depend not on all the guys before, but only the guy just before. So instead of having dependencies all these guys, we only have the dependencies like this. So this is what we call a Markov chain. Great. So now what we kind of introduce here is hidden variables. So if I make an example of this, let's do this here, then actually let's do it over here, then I might actually have hidden states like so I mean there might be something I don't observe which is actually influencing my observables. So these were the observables of my example before, here, rain or sunshine. So there might be some kind of state that influences the particular weather, like high or low pressure. So it might be that there also was some variables like hidden high pressure, low pressure, high pressure, high pressure, high pressure, low pressure, low pressure. And in this kind of sense, there's dependencies between these guys, and that for each of these guys there's some probability of it being rain or sunshine. So introducing these kind of hidden variables, as C1 through Cn, we kind of arrive at what we call a hidden Markov model, because we have hidden variables. Great. So this is what I wanted to talk to you about dependency graphs. In the next video, I'll talk to you briefly about decoding and computing stuff in a hidden Markov model.